Hi everyone, my name is Yahav Bechavod. I'm a PhD student at the Hebrew University. This video is about joint work with Christopher Jung and Stephen Wu. This is somewhat of a generalization. However, on a high level, the majority of the work that we've seen in algorithmic fairness pertains to statistical fairness guarantees. Some consider a rich collection of possibly overlapping subgroups. However, even these notions are limited in the guarantees that they offer to individuals. Here's an illustration taken from Kearns et al. Let's assume for the sake of the example that we wish to equalize acceptance rates. We can see that the criterion holds for groups defined by a single feature. However, as we move to a final level by considering intersections of features, things break completely. This was only a simple illustration, and we note that even group fairness definitions that are defined over a rich collection of possibly overlapping subgroups may still break when considering the individual level. A different notion of fairness that was introduced by Work et al. Aims to provide guarantees on an individual level in the form of a Lipschitz-like condition on the predictor, which is inspired by the assertion that similar individuals should be treated similarly. A crucial part of the definition hinges on the availability of a similarity metric between individuals in the context of a specific task. This metric, however, is often unavailable. It is also often unclear how such a metric can be acquired in the context of many tasks. Our approach suggests a solution to this problem by employing the human fairness auditor, an expert in the relevant field, providing the algorithm with fairness feedback. What type of feedback? Well, we can try and ask the auditor for the exact formula that measures fairness in his mind, but this may be very difficult for him to answer. Another suggestion is to ask him for the exact distance between any two individuals, but this is still a bit too hard to specify, especially for a large number of queries. Finally, what we suggest instead is querying the auditor for fairness violations. Can you spot a pair of individuals who are similar, but were treated very differently by the algorithm? This is inspired by the idea that while the exact formula of fairness might be hard to specify, the auditor instinctively knows unfairness when he sees it. Our setting is the online contextual learning setting, where on each day the learner deploys a policy, then k individuals arrive and are predicted using the deployed predictor. Finally, the learner has two types of feedback: the true labels of the individual fairness, the true labels of the individuals, and fairness feedback from the auditor, indicating whether or not the deployed predictor induces a fairness violation on some pair of the individuals who arrive. And this process repeats itself between days. First, I'll give a high-level overview of our results. As we've seen, the problem that we're trying to solve is the online fair batch classification. First, we introduce a regret-preserving reduction from the fair online learning setting with additional auditor feedback to the standard online learning setting by constructing a fake stream of examples. The upshot is that given any algorithm for standard online learning, we can translate its regret guarantees to upper bound both the accuracy regret, but also the number of fairness violations in the original setting. This holds true for any adversarial arrival of individuals. A second result is, if we had the assumption that individuals are drawn from a distribution, that we are able to prove generalization guarantees for both accuracy and fairness for the average policy over the run of the algorithm. Now that we've seen the high-level results, we will see the main results in more detail. We'll start by formalizing the human auditor model, then move to the online fair batch classification setting. Then we will see how to achieve no regret guarantees in an adversarial setting. And finally, we will see how to additionally achieve generalization guarantees in the stochastic setting. Let's first introduce some notation. X is the instance space, Y is the label space. H is a hypothesis class of binary predictors. We assume that age always contains a constant predictor. For the sake of learning with individual fairness constraints, it will be useful to consider all the convex combinations over H, which are probability vectors over the base class. We denote this set by delta H. The misclassification loss we consider is the 0-1 loss, and we generalize it for convex combinations of predictors or policies as the expected loss over base classifier. Next, let's have some definitions regarding our fairness constraints. We assume that the auditor implicitly has some distance function that measures similarity between individuals. It is important to stress that D does not have to be a metric and does not have to obey the triangle inequality. This function only has to be a non-negative and symmetric. We say that a policy has an alpha fairness violation on a pair of individuals x and x prime if the difference in predictions that they receive by the policy is larger than the distance between them plus some slack of alpha. We next formalize the auditor. An auditor J alpha takes two inputs, a set of individuals and a policy, and outputs the following. If there exists a pair of individuals in the reference set on which the policy has an alpha violation, it returns one such pair. If multiple pairs exist, it may return any of such pairs. Otherwise, if no violation exists, the auditor returns none. Let's quickly move to formalize our problem setting. In the online fair classification setting, as we've already seen, the learner commits to a policy at the beginning of every round. Then k individuals arrive, possibly in adversarial manner, and are predicted according to the selected policy. The auditor then examines the predictions, and the learner is finally provided with both the true labels of the individuals and fairness feedback from the auditor. And this process repeats itself between days. This is a formal description. Note the two types of losses at the end of each round, the misclassification loss and the fairness loss. The first type of loss is the misclassification loss of the policy on all k individuals. The second type of loss is defined to indicate whether or not there are fairness violations by the policy in a specific round on the individuals that arrived at that round. Now we will see how to achieve no regret in the online fair classification setting. First, we formally define the notion of regret. We will say that an algorithm has a regret guarantee that we denote by regret upper L, A, Q, T. If for any sequence of arriving individuals and reports by the auditor, the difference in the loss incurred by the algorithm and the infimum of the loss of the comparison class is smaller than regret L AQT. In short, that means that the algorithm achieves the optimal performance comparing to any policy in hindsight, up to some term. Now that we've defined regret, the first natural question is what class of policies are we comparing the performance of the algorithm to? We'll compare the performance of the algorithm with the highest performing policy, which is also individually fair, on each round separately. Another suggestion could have been to compare performance with a more restrictive class of policies, which are individually fair across rounds. However, that seems to be hard to satisfy. The algorithm has no information in the beginning and thus has to commit to possibly suboptimal policies deployed at the beginning, which could result in linear regret. So the baseline Q alpha that we compare ourselves to are all policies that are alpha fair within each round. We will only penalize the algorithm for slightly larger violations of magnitude alpha plus some epsilon. You can find the full algorithm in the paper, but we will give an intuition. The idea is to reduce the problem setting that we have of online learning plus fairness to standard online learning. We do so by translating the original stream of samples combined with the readings of the auditor to create a fake stream of examples to the standard set. The key is to encode both types of losses, the misclassification and fairness loss in the original setting. In a standard 0-1 loss in the standard setting, we reduced it. The upshot is that given such reduction, we can apply algorithm for the standard setting and use its regret guarantees to upper bound both the misclassification regret and the number of rounds with fairness violations, comparing to the class of fair policies. Here's one example of the guarantees that are provided using one such algorithm, namely context FTPO. This is an Oracle efficient algorithm in the standard setting, meaning that it runs efficiently given access to an optimization oracle. We can see the upper bound of root t times log of the size of the hypothesis class for both. Let's recap what we've seen so far. We've started with the online fair classification setting and have seen how it can be reduced to the standard online classification setting, inheriting the regret guarantees of any algorithm in the standard setting. In the final part of the talk, I will discuss generalization. So far, we've operated under the more general setting of adversarial arrivals. However, realistically, people are not expected to arrive in an adversarial manner, but rather according to some underlying distribution. Therefore, in this section, we will assume the existence of such distribution. Note that all of our more general results still hold under this assumption. The question we will try to answer in this section is whether, given the setting and construction that we have seen in the previous section, we can output at the end of the algorithm's run a policy with both accuracy and fairness guarantees on the underlying distribution. In practice, this would be particularly useful since we might want to at some point deploy a specific policy and wish to do so only for a policy with proven guarantees. Let's see. At least intuitively, accuracy generalization appears to be a much easier task since we have full feedback. At the end of each round, the learner receives all of the true labels associated with the arriving individuals. Fairness generalization, on the other hand, seems more challenging. The main reason for that is that for fairness, the feedback is limited. In the worst case, the fairness feedback on each round may only pertain to the policy that was actually deployed in this specific round. We also note that the auditor only reports a single violation out of possibly multiple ones, and that the auditor may act adaptively in selecting which pair of individuals to report. Given the points in the last slide, it seems that we cannot apply a standard uniform convergence argument to prove fairness generalization. Instead, we choose to consider the average policy over the run of the algorithm. We will next see how this will allow us to prove generalization using a different argument. Here is a first statement pertaining to the accuracy generalization of the average policy. The bound that appears here stems from the standard online to batch conversion. And we can see how it uses the regret bound of the online algorithm to upper bound the generalization error. Next, in order to discuss fairness generalization, we will first define it formally. We say that a policy pi is alpha beta fair on distribution D if the probability taken over pairs of individuals according to D of pi having an alpha fairness violation is at most beta. Here is the statement for fairness generalization. Let's parse it slowly. The starting point of this statement is considering all of the policies that were deployed during the run of the algorithm. For each such policy, pi t, let's assume that the probability of this policy of having an alpha fairness violation on a randomly selected pair is at most beta t. Intuitively, the sum of these beta t's cannot be too large. Otherwise, that would be a contradiction to the regret guarantee of the algorithm. Hence, the sum of these betas has to be bounded. We will see now, however, that it will not be possible to give a meaningful upper bound to the probability of an alpha fairness violation of the average policy based on upper bounding the betas. And we will thus have to relax the target violation size to a slightly larger quantity. Here is the reason. If we consider alpha violations of the average policy, it is easy to see that in the worst case, the average policy could have an alpha fairness violation anywhere in the distribution over pairs where any of the deployed policies has such violation. The upshot is that the upper bound in this case will have a probability of alpha violation that is the sum of betas. Considering that we will bound the sum of betas later by the regret of the algorithm, this is not good enough. What we will do instead is interpolate between alpha and beta. We will increase the regret violation size slightly from alpha to alpha plus some q over t, where capital T is the number of rounds and q is some integer. And see how this drastically improves the bound that we can give for the frequency of such violation by the average policy. The lemma reads as the previous one with one change, there is a 1 over q factor in the violation frequency term. The intuition for the proof is the following key observation. Considering slightly larger violations of alpha plus q over t, in order to cause an alpha plus q over t violation of the average policy on a specific pair of individuals, at least q of the deployed policies during the run of the algorithm must have an alpha fairness violation on this pair. The next step is to upper bound the sum of the betas by the regret guarantee. The simple intuition for that is that in order for the regret guarantee of the algorithm to not explode, it must not deploy unfair policies too often. Since we've seen that this would result in high unfairness loss, which is part of the joint loss that the algorithm attempts to minimize. Using these two steps, we can finally get the generalization bound for fairness, which has a rate of roughly 1 over q times the regret plus a root theta. Finally, using an instantiation of a specific oracle efficient algorithm, we can achieve the following generalization guarantees. Remember that capital T is the number of rounds in the run of the algorithm. We get a rate of root log the size of h over t for accuracy, and a rate of t to the minus 1/4 for the size of fairness violations and the frequency of such violations. To summarize, our approach removes the classical metric assumption. Auditing is made easier where the auditor needs only to report a single fairness violation if any exists. Our results come with no parametric assumptions on the hypothesis class or the similarity function, and our algorithms can be implemented using Oracle-efficient online learning algorithms. In the adversarial arrival setting, we guarantee no regret for both accuracy and fairness. And in the stochastic setting, we can additionally prove generalization for both accuracy and fairness for the average policy. Here's a short comparison with prior work. Note that our results do not require the similarity function to actually be a metric. The type of queries to the auditor are regarding violations rather than numerical distance queries. And the auditor in our formulation is only required to report a single fairness violation rather than all violations. Here are some key takeaways. First, we've seen how the classical metric assumption that is made in the context of individual fairness is actually not necessary. We've also seen how there's no need to directly learn the similarity function. We can instead only learn how to not violate fairness according to it. We've seen how the concept of a human auditor allows us to directly incorporate humans' perceptions of fairness into the learning process. And finally, and maybe the most surprising, we've seen how a relatively weak form of feedback from the auditor is sufficient to learn with accuracy and fairness guarantees. The full paper is available on arXiv. Thank you so much for watching.